Good morning, everybody. It's my pleasure to introduce Professor Jacqueline Nagel from James Madison University. She's going to talk about teaching biomimetics with CK. She's an engineer, academic, and consultant at James Madison University. She's a she's a full professor in the Department of Engineering. She earned her degree in mechanical engineering from Oregon State and her bachelor's and master's from manufacturing engineering and electrical engineering from Missouri University of Science and Technology. As a multidisciplinary engineer, her diverse areas of expertise are bio-inspired design, mechatronic systems, and manufacturing automation. She's internationally known. Actually, I met her in Paris, not in the US, even though we are only 200 miles apart from where I live. Given talks, webinars to Society for Women Engineers, INCOSI, NASA, and universities in Canada, France, and US. She leads practicing engineers and organizations through the process of taking inspiration from nature to solve problems in her consultancy. With that, I will give it to Jacqueline. It's a pleasure to have you, Jacqueline, in this forum. And as I said, you're always welcome to join us anytime.
Great. Thank you so much for the invite and this opportunity. So thanks so much for that introduction. Maybe what my introduction doesn't say is that a big part of my research is focusing on the practice and the pedagogy of biomimetics. And so I'm really focused on understanding how do people do biomimetics, and then what are tools and frameworks that I can create using different theories, a lot of times theories of design, that can help people intentionally get to a bio-inspired design. So that is the main thing for my research, is helping people intentionally create some design or solution with inspiration from nature. So let's get started. Let's just make sure we all have a good understanding of these different topics. So let's start with biomimetics. And this is really the process of studying nature to solve human problems. This whole idea of taking inspiration from nature was really popularized in the 1990s when this book, Biomimicry, written by Janine Benyus, came out. And it really set the stage for people to expand their thinking, like, oh, this is happening in the world around us. We need to pay more attention. And so what's happened, interestingly, is that a whole bunch of terms have come out of this. So biomimicry is a main one. I would say it's sort of like a umbrella term, and it really is trying to define the philosophy and this interdisciplinary design approach of taking inspiration from nature. And the Biomimicry Institute that Janine Benyus also helped found, she always puts biomimicry in this context of sustainable development. And so that's biomimicry. But then these other terms have popped up across the world. So biomimetics, the one I'm using today, that's more of a broader term. You find it in the United States, but also across Europe and Asia. And it's very similar to biomimicry. So it's this interdisciplinary cooperation of biology and technology. And here it's put in the problem-solving context. So solving practical problems through learning about and analyzing biological systems. And then there's another term called bio-inspired design. And this one's really been adopted by the engineering community, probably because it has design in the title. And it's also BID for short, if you ever heard that. But again, it's this interdisciplinary design approach, so taking inspiration from different sources like biology, design, and understanding the principles to address human problems. So you should be seeing a theme here. And the final term, bionics, this one is slightly different from the other ones. This one is really about replacing or replicating something in nature. So think about a prosthetic limb, so an arm, a hand, a leg. So trying to recreate what was lost, essentially. And so now I want you to focus on these blue words and notice that regardless of where you fall in the terminology, it's all about learning from nature. So nature as a model, understanding through functional analysis and abstraction, interpreting principles, understanding biological functions. So learning the biology is really central here. And that's what helps designers arrive at that technical innovation. So it's not what we can extract, but what we can learn. And there's a whole variety of things that we can learn. There's the physical aspects, the things that we can see, such as the forms, structures, surfaces, materials. But then there's also the things we can't see, those non-physical characteristics. This would be more like a functionality or a process, some kind of system interconnection or a way that an organism communicates. And so what we find is that when biomimetics is practiced correctly, the solutions are efficient, economic, elegant, like the two examples I have here with the Pax impeller and the end cycle swarm energy management. Both of these are reducing energy usage by a sizable amount. But then there's actually a downside that if it's practiced incorrectly, you actually aren't doing biomimetics. You end up imitating nature, and then that's a whole different area. Let me show you what I mean. So there's these spectrum of biological words, and they all start with bio something. So let me show you. On the left, you have the situation where you're using nature. So this is bioutilization. So the example I have here is a biosensor. So there's some kind of protein or enzyme that when a substance like blood, let's say, is mixed with it, then the sensing happens. But you need that biological component like the enzyme or the protein. The other end of the spectrum is something that we see more often, and that's the biomorphic. So it looks like nature, but it isn't inspired by. So the example here is a wind turbine that looks like a tree. So you can see here in this landscape that there's one tree that looks a bit different, and that's because it's artificial. But it's a wind turbine, and it's made to look like nature so that it can integrate into the rest of the landscape. But it doesn't take any inspiration from how the tree works or functions or processes light or anything. It just looks like a tree. And so that's biomorphic. So it's interesting here that with biomimicry, biomimetics, bioinspired design, if you're not doing that component of learning and you start to incorporate the nature into the design, you actually are doing something else. And so that's a bit different when we talk about design, because usually design is this creative process and you want to explore and try different solutions. But in this field of biomimetics, it could actually not work out in the way that you anticipated, right? So you end up in bioutilization or biomorphism. So what I want to help you all with today is really staying in the middle here, biomimicry, biomimetics, and bioinspired design. And so inspiration can actually come from a variety of sources. there's so many examples now of the observation of just something happens. Somebody has an aha moment. Velcro is or hook and loop is the most commonly cited example of this, of, you know, a person walking through the woods, happened to also be an engineer, noticed something sticking to his dog's fur, started to study it, understand it, and came up with an idea, right? So it just happened by chance. Whereas, you know, the other end of the spectrum, like in the Marisol display, you know, this is a technology that took years of dedicated research to understand butterfly wings and how they are making their vibrant colors. These butterfly wings don't have dye in them. It's what's called structural color. So the color comes from these structures here that have a spine with the straight lines coming out. I like to call them Christmas tree structures. That's what I think of when I see those. But the way the light interacts with those causes it to refract and reflect. And so then the wavelength that exits that structure is the color that we see. And that's how we get those vibrant colors without any dyes. But this took years of research to understand what's going on here with the butterfly wing. And so these are definitely the extremes of finding and applying inspiration. And so my work is right here in the middle, trying to create tools and frameworks that can help someone systematically explore the design space, but reduce the amount of time and effort to creating that intentional bio-inspired solution. And so the process that I walk people through is shown here. So you start with a problem. You have to understand the problem, no matter what you're designing, whether it's bio-inspired, biomimetic or not. You have to understand the problem. But a key step here is then reframing that problem to better frame it so that you can find the biological inspiration. And so then that helps with identifying suitable biological organisms that can help you solve the problem. And then transferring that information requires analysis and possibly more abstraction of the biological information, which can then be applied. And so this is 5 steps, but you'll see the dashed line there and it says embodiment. So in this process, these are 5 steps of the early phases of design, and then you would transition into more traditional engineering design tasks of prototyping, material choice, testing, and so on. So really detailed analysis. So this is just the front end of the design process. So really coming up with that core idea. But what I've discovered over time researching and teaching in this area is that a lot of people get hung up here in these last 2 steps that I've colored in orange now, the transfer and apply. And so a feedback cycle starts here, a feedback loop. And it requires iterative knowledge building and connection making. So somebody will get through to apply and realize, well, I don't know how to make this. It's not clear to me. So then they have to go back to transfer and learn a little bit more about the biology, try to clarify their concept, and then apply it again. And they do that a few times. So again, that learning the biology here is really central. But even some folks who realize and can get through this process, a lot of people get stuck. Whenever you're working across domains, a lot of people get stuck, right? Because there's a lot of information to manage. And so noticing this, I wanted to create something that could better help my students get through this process of bio-inspired design without getting stuck. And I learned about CK theory, or concept knowledge theory. And I thought, oh, this will be really useful to help with this process and help students and professionals, novice designers in this area of biomimetics get unstuck. So it can really help facilitate that discovery. So let's talk a little bit now about concept knowledge theory. So there's two spaces, the C space, the concept space, and then the K space. The K space is filled with information where the information is known or it's prepositions, they have logical status. This is something you could look up in a book or some concrete knowledge, a theory, a law, something that's well known. Whereas the C space is the opposite. This is a place for things that are undetermined, questions that are unanswered, and the ideas are still being formulated. But what's interesting about CK space, or I'm sorry, CK theory is that there have these operators. So there's 4 operators. You can move between the K space up and down, so K to K. You can do the same in C space, C to C, but then you can transfer back and forth between the 2 spaces. So as you learn something in K space, you can use that to affect the C space and vice versa. So when you learn or expand an idea in the C space, you're like, oh, this is interesting. I need some more information. Can I break this down further? And then you go back to the knowledge space. And so there's this iteration that's happening of building these transformations to really expand out that C space and fully explore the knowledge space. And so there's this connection building that happens, and that can really facilitate some innovation. And what's also nice about CK theory is it's adaptable and generalizable across engineering and scientific domains. So it's not specific to a specific domain. And so that allows it to be adaptable to a variety of problems. So if we think a little bit more about the 2 spaces, it sounds like somebody has unmuted themselves. I don't have control over everything since I'm sharing my screen. Can somebody help with muting the sound? Thanks. And possibly removing the blue streak on the screen. So going back to CK space. So the knowledge space, it really facilitates this digging deeper of trying to better understand a particular area and then drawing connections within knowledge itself. So connecting, say, mechanical engineering to electrical engineering. And it's also where you start to learn unexpected things, and they can use that as a launching point or a springboard to come up with a new idea. And it really supports the biology-driven approach. Where the concept space really allows that exploration, and you can pose questions or hypotheses and then test them. You can create ideas and start to break them down and better understand them and explore them. And then you can also create a path so you can follow how you got to this point. And this phase really supports that problem-driven approach. And this is what happens most often in engineering. You're given a problem and you have to find a solution. And so my work in applying CK theory is really based off of the work by Salguero. They did an analysis of bio-inspired designs, trying to think through and understand how people are arriving at inspiration from nature, and could they explain it using CK theory. And so this paper, this is the framework that they were using, and this really provided the foundation for the work that my research in this area of applying CK theory to create instructional materials for teaching engineering. And so this is one of the instructional materials that I created. It's called the BID Canvas, so Bio-Inspired Design Canvas. And it's this visual guide to structure the process of biomimetics. Because as I mentioned before, it's a design process. There are some feedback loops. People can get stuck wondering, am I doing this right? And usually the answer is yes, but it feels messy. It feels unstructured, which can then lead to uncertainty and worry. And so this canvas helps to structure all these processes for biomimetics and really helps to build those connections across engineering and biology to then allow the expansion of the concept space to create a variety of interesting solutions. And because this work was supported by an NSF grant, everything is freely available on my website. So this was just one of the instructional materials. There's also a teaching module and a set of learning activities that go with the BID Canvas to help scaffold this process of discovery for novice engineering designers. So it really walks students through what is biomimicry, what is bio-inspired design, and then how can we go through this process of discovery to arrive at a biologically inspired solution. So we created these instructional materials, but then we wanted to know, do they work, right? So a simple question. We have grant funding, we need to report results. So first, we did a study. We wanted to know, do these, so we hypothesized that taking CK theory as a way to create these instructional approaches, these instructional materials, it would help us meet our research objectives. So that was the first check that we wanted to do. So in order to test this, we had a set of students at two institutions, so James Madison University, where I'm at, and then one of my colleagues at University of Georgia. And so we gave them that module that I showed on the prior page. They had to go through the learning activities, and then they had to apply bio-inspiration to a specific project they were given. And so all the students were using the CK theory-based materials, but we never, so a key piece of this is we never told them you are doing CK theory, right? We didn't want to burden them with thinking like, oh no, I have to learn a new theory, or something like this. So it was just, here is a way to structure your process of taking inspiration from nature. So we never told them it was CK theory related. And so we performed this multi-institution study, and these students were all second-year students, sophomores. And the project we gave them was to create a propulsion mechanism for a human-powered vehicle. And so what a human-powered vehicle means here is some kind of vehicle that's not a two-wheeled bicycle that a person with a disability could ride. So it may have 3 wheels, it may have 4 wheels, and it may have a different configuration. But the key thing is it's not a two-wheeled bicycle, because our client could not ride one of those, which is why they need a different kind of vehicle. And so we had the students think about this particular problem. We gave them the canvas and then all of the other instructional materials. And then once they were done, we had them answer 6 reflection questions. And so once we collected all this data, then we were able to do the qualitative analysis. And so that's what's shown here on the right. So here's an example student response. They have the 6 questions. What did I learn about the content? How did I learn it? What am I going to do with it? And so that's the content. So that's the bio biomimetics. But then there was the process. What did I learn about the process? How did I learn the process? What am I going to do with the process? And so the triangle here is showing how the qualitative analysis was applied. First, we looked at their response and we found meaningful units, and that's what each of these colored boxes is representing. So the yellow is a meaningful unit, the pink is a meaningful unit, and so on. And so now that we have the student response identified as meaningful units, then we can start to code them. Then we can start to group those codes into categories. And then finally, we can group categories into high-level themes. And so it looked kind of like this. So this was a result. So you can see the top three are that question about the biology, the content, and then the bottom three are about the process of biomimetic design. And then here are the themes. So we don't have the really detailed stuff, but really just the high level, the themes. And then there's a number that says how many categories support this particular theme. So you can see the really strong ones versus the weaker ones. So if we look at the top question, what did I learn about the contents related to biology? You can see that the really strong themes here are cross-domain linkages. So finding those connections between biology and engineering, which is really great because that was one of the key things that we wanted students to be able to recognize through this process. And that they found value that they could learn from nature or biology. That's also a key one here. So just changing their mindset of, oh, there's inspiration all around us. I can take inspiration from something out my window, right? If we look down at the design, so again, that first question, what did I learn about the process of doing bio-inspired design? That first one is really, really strong. So value the inclusion of biology. So again, value is a really strong theme here, which is good, right? Changing that mindset, opening up the possibilities. But then the next one, which is also really, really strong in that they realized that they could do it, right? They could transfer information from one domain to another to help solve their problem, right? So they are now convinced that I can do this and it has value. And so these are really, really strong results. So we were very excited about this. And then there was an unexpected result, which is really exciting. So we go back to that first question. There was a student that expressed, well, I actually learned more about engineering because of biology, right? So they were seeing biology as a way to understand a phenomena that was happening in engineering. And because biology is typically taught pre-college grade, so like high school, they already had that information. And so they can use it as a bridge to better understand what they were learning in their engineering classes. So that was really exciting as well. So lots of great things came out of this qualitative analysis, and this shows us that it's working. And so here's an example of a student work. So again, they're trying to work on a propulsion mechanism for a human-powered vehicle. And so they were thinking about it with a pedaling motion versus without, right? Because the existing solution is to use a gear with a chain and pedals as the input, so this rotational motion. But that can be a good challenge for someone with a disability. So they thought, well, how do we do this without pedaling, right? Let's lower the hurdle even more. And they took inspiration from a frog and the way the frog legs move when hopping. And so it's a motion with both legs are moving when the frog hops. And so they thought, okay, well, let's use 2 feet in the propulsion mechanism. And it's this motion that's related to a leg press. All right, so they're seeing connections in the knowledge space. They're like, okay, a frog works this way, it stores energy, it releases it. What can I connect that with up here in in engineering. And so they had leg press, trampoline, swimming, rowing. So lots of interesting things there. And then using this to come up with some rough ideas. And then they selected the first one because we can see their design path and how it's evolving. Okay, so this is really good, really strong. So we're happy, but now we wanted to know a new question. So now we wanted to know, do these instructional materials based on CK theory improve the quality of designs? So we know that they support making designs, making solutions, but we want to know about the quality. Is it better than other approaches? And so again, we have our students at James Madison University, but this time we split them up, roughly half and half. It worked out really well. So 2 sections that were larger all got the CK theory-based approach. And then 3 sections that were a little bit smaller, we actually gave them instruction on the Biomimicry Institute approach. So if you've ever seen, it's the design spiral. And we used all the same teaching materials with slight modification to introduce the Biomimicry Institute. But the CK approach was the same as the one before. So we have our study, it's all set up. And so the way that we did the analysis this time, it had additional layers. So we had the instruction, you see the Biomimicry Institute, that wheel there, the updated version of the design spiral, and then the BID canvas, so the CK theory-based approach, sticking with the same problem, human-powered vehicle. And then once we collected the data, we did evaluation. We used 4 different metrics, and they all had flowcharts similar to this. So it's a set of 3 questions and then a 0 to 3 answer. And all of the concepts that came out of the study were scored by at least 2 people. And then we ran statistical analysis using those scores. And here are the results. So we found that our hypothesis that the CK theory-based approach would produce higher quality solutions to be true. And we found it to be true with statistical significance. So we had the 4 metrics: biomimicry, feasibility, novelty, and practicality. Feasibility here, is it possible to be made? Novelty, is it unique to the set of concepts within the pool? So not unique outside, in everything, but just amongst the group of concepts. And then practicality was more in the sense of the user rather than, say, manufacturing or something like that. So could the user feasibly use it, given that they have a disability? And so what we found is that the students who got the Biomimicry Institute approach, their results, their concepts were closer on that spectrum of biomorphism, so more imitating nature. So the results kind of looked like frogs. And so here's one example here, this mechanism with some pedaling, but then the legs of the vehicle are definitely frog legs. Whereas the students in the concept theory approach, concept knowledge theory approach, okay, their results were more inspiration. So really digging into understanding the physical and the non-physical characteristics and finding those connections and then applying it to create an inspired solution. Right, so let's look at that one in a little greater detail. So this particular student, they had thought about propulsion from an assistant assisted versus non-assisted context. So one of the things that we noticed with some of our clients is that in that rotational motion, they can do it, but they sometimes will stall out when the pedals are straight up and down in either way. And so this particular student was thinking, well, what about if the design had an assist? How could I do that? And so that is really what framed their propulsion system design. And so again, they were studying frogs, learning about how frog legs store elastic energy, contrasting that with the way gears work, and really finding a lot of great connections between this property of the frog and what already exists in engineering. So this particular student identified that springs store elastic energy, rubber can do this, crossbows do this, that leg press machine showed up again. And so then these connections were what really helped to come up with these different rough ideas. And so again, the first bubble was selected as the idea to explore further. And they incorporated these elastic bands. So they're twisting. So as the pedals are rotating, so they're storing some elastic energy, and this will become the assist. So that's everything that I studied in depth with students. I've also used these tools and frameworks with industry professionals. And so here's a paper that came out recently in 2022. I exposed industry professionals that do consumer design of home goods, and they got to learn about not only bio-inspired design, but the BID canvas, a search tool that I created, the engineering biology thesaurus, and then a visual analogy sketching approach. And what was interesting about this particular study is that the professionals valued everything. Right? They found value in all of these different tools, but the one that really stood out amongst the four was the canvas. And it really comes down to it was the most flexible, right? If you think about somebody who's working in industry, they have a workflow or work stream, and they have to fit their projects within a certain time. This one really allowed them that flexibility to work through the bio-inspired design process, not get lost, but then they could also backtrack if they needed, or if they learned something new, or they had to set it down and come back to it. You know, they could really follow what they had already done. And when these particular engineers also commented, you know, we already have a whole variety of tools that we're using in our design process. And so this allowed them to bring those existing tools into a new process. So in this case, the bio-inspired design process. And so they just really appreciated and valued that flexibility. And you know, I thought, you know, long term, if I'm going to use any of these tools again, it's probably going to be the BID canvas. And I guess to further make this point, I got to teach a course last month, a week-long course with fifth-year students in France at EPF. And out of all of the skills and the tools that I taught them, the BID canvas was also the one that they commented the most on. And they really valued this. You know, at the end of each session, we did a brief reflection of what's something you learned or appreciated from class today. And the canvas was mentioned every time. Maybe not by the same people every time, but it was consistently the thing that students were commenting on. So that was also exciting to hear about. So in closing, I would like to say that biomimetics is a practice of problem solving. It has its own set of skills, it has its own process, it has its own set of frameworks of tools. And it can result in technical innovation. And the goal here really is getting to an inspired solution rather than one that's imitating nature. So don't let the term biomimicry confuse you there. It's really about inspiration over imitation. And I found success with CK theory and using that as a framework to help novice designers, both students and industry professionals, people who are new to bio-inspired design and biomimetics, really structure their knowledge transfer and get to that successful bio-inspired solution. And through the variety of studies that I've been able to conduct, I have conclusive evidence of the learning impact of these instructional materials. And it really shows that there's support for the pedagogy of biomimetics in engineering education. And then finally, just an invitation that, if you're looking to incorporate biomimetics into your courses or teaching, or maybe it's industry training, please reach out. I have a wealth of materials beyond just what's on my website. So that was the NSF funded stuff, but then, that's a module. I have a full course that I offer. And so if I can help you in any way, please reach out. I'm open to sharing my materials. And so with that, I will say thank you for listening. Thank you for your time, your attention, and
Thank you very much, Jacqueline. That was
yeah, you're
really
welcome.
wonderful. And also, I was going to see this earlier. I suppose I didn't in Paris. In any case, I think what you have done is really fantastic in the sense that not only you have produced teaching material, but also all the instructional structures which could be propagated to other people. And this was one of the
Yes,
reasons I really wanted you to come and give this talk. And we will invite you another time to talk about the kind of things the students have done over in your courses using
sure.
this I remember you talking about the whale and various other devices that came up uh, in your previous presentation, the ant hill and few other
Oh,
bio-inspired
yeah.
building, right? Anyway,
Yeah, that's true. I did not go through a wealth
yeah,
of
yeah, yeah,
examples. There's so many out there. It's very easy to find them now.
yeah.
Yeah, I really focused on the instructional
No,
materials
you have
today.
all of those material. No, I'm glad you did that. With that, I open up for questions. I'm sure there are people with questions, and maybe
Yeah,
Sudhir, you want to start?
I'll
Yeah,
stop sharing so
thank
people
you,
can
sir.
see me.
Jacqueline, thank you for your presentation.
Oh, you're welcome.
Just a quick clarification. There was one slide where you showed a statistical data on biomimicry versus using CK theory, right?
Mhm.
In that, the last item was practical, and in both the columns you had said none. So could you please clarify what did you mean by that?
Yes, and so that was with respect to the user practicality. Could the user practically use this
Yeah,
device,
so there,
this
the
vehicle?
question, the question I had in relation to that was when implicitly CK theory pushes you towards more practical solutions. So why is it that that element came out as none?
Wasn't it much
Uh,
smaller study in the Georgia Tech case? It was a much just
well,
integrating a piece, right?
so if you think about statistics, right, it's looking for a difference. And so what this doesn't say is that they're not practical. It's just there's no statistical significance between the two groups. So what
Okay,
I would
so
read this as is they are practical. There just wasn't a big enough difference in the
okay,
practicality between the two.
okay, because my understanding is that there is a lot more emphasis on leveraging existing knowledge base
Right.
and not deviating too much towards imaginary concepts when we bring in
Right.
CK. Right. Yeah.
Exactly.
Thank you.
You're welcome.
Sham?
Thank you, Jacqueline, for a very interesting presentation. Of course, biology has inspired, I'm told, people since ancient times have tried to do mimicry of birds by attaching wings to their arms and jumping off tall buildings to try to fly. And I guess that will fall into biomimicry, I guess, of some sort. Didn't work, but modern airplanes do look like birds in some sense, though mechanism behind them is quite different. I have a couple of a question and a comment. I would imagine that various approaches that you talked about, your focus was on, in your presentation, on this is better than this. And could it be the case that some approaches are better for some applications, while others are more fruitful for other applications? And students need to learn how to select the approach they follow from their toolbox, depending on the nature of the problem? Or is it the case that you find that some approaches are clearly dominant over other approaches, and the other approaches should simply be ignored or rejected?
Excellent question. So I can answer in two ways. The one about the better than, so I needed some data to show that what I was creating was improving the quality. And so if my baseline was just whatever they're already doing, of course I'm going to show that this is an improvement. There's a number of studies already in the literature that show if you do any kind of intervention, you get better results. So I didn't want to do just what they were already doing. I needed something that was comparable. So that's why I chose another really well-known approach. So that's the Biomimicry Institute. They have everything out there on the web. It's freely accessible. People have seen it. They've looked at it. It's available. And so that's why I chose that one. And then to follow up on that, you asked, well, what about, is it just problem dependent, or, you know, could somebody just be really good at this one, but not so good at this one because of their training? And my answer to all of those questions are yes, right? So I fully agree with you in that, you know, when you're exploring the design space, there's so many different tools for doing concept generation. You have to pick the one that works for you. I can't really say that one tool is better for a specific type of problem, but I definitely believe that there is a tool that works better for you and your own workflow, your own philosophy, your own way of thinking, your mental models. And so those are the ones you tend to use more often. They make sense to you, right? So you're going to apply them more often. And there are cases where bioinspiration just doesn't work. That's okay, right? It's one of the many ways to do problem solving. So I completely agree with your point there of, you know, what if you try something else? And that's what I try to help my students with, is like, there's so many ways to go about doing design. You have to find what works for you. And they don't really like that because I didn't tell them you must do blah, 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 blah. You know, like, it's more of, you have to try a bunch and figure out what works.
Thank you. My just very brief comment, I hope you don't think it's nitpicking, but it's about how we present our statistical results.
Sure.
When we use hypothesis testing framework, we can reject a null hypothesis in favor of an alternative, but we can never reach a conclusion that a particular hypothesis is true. At least that's my understanding of a statistical theory. And I just want to mention it. Thank you.
Yes, thanks for.
Anybody else in the audience to ask questions? Who want to ask any question? Please open your mic and go ahead. Don't see anybody. Okay, I have a couple of questions for you. Oh, yeah. One of the questions I have is, just give me a second, somebody. See, when you started using CK, you used it as a general framework. So from your experience of combining biology and engineering in this case, it could be any other two disciplines or any other multiple disciplines that could come into play in creating this space, right? In some sense, what CK theory allows you to sort of sort out in your head is to separate and organize the concepts on one side, and then what you know on the other side, and what you need to find out to do what you want to do, right? What you would like to do in some sense. It's that gap between the two, how the movement between the conceptual space and the knowledge space back and forth is the fundamental pedagogical message that you are conveying, if I'm correct. Yes, biology is one space, but it can also be used in other spaces as part of the way they think.
Yes, absolutely. So the BID canvas is organized specific to this process. And so the bottom box is the biology, and then the top is labeled traditional, so it's everything else. So I'm pulling out a specific type of knowledge because I want students to really think about it and learn it, and put the necessary attention on it because it's so critical in getting to an inspired solution. But yes, you're right. It could be anything else. It could be law or cooking, food, agriculture. Absolutely.
No, the reason why I want to point that out is, as a design theory, it has a powerful rhetorical way of sorting our thoughts. And that's what helps us in a way to do this in the fashion you have been able to do in a very successful way in biomimetics. And of course, our Paris colleagues have done similar things with high school as well. So thank you very much. And if there are no more questions, Sudhir, any other thoughts or questions you want to?
I'm fine. Thanks, Jacqueline.
Anyway, thank you very much. Yeah, thank you very much, Jacqueline. And once you're back in James Madison, maybe I can come by and see you there and what you're doing. That would be wonderful.
So we might mention that the video will be on the website.
Yeah, the video will be on the website soon. I'm backlogged, but I'm getting there slowly.
Great. I really appreciate the opportunity and the invite again, and thanks all for attending and your great questions. I really appreciate it.
So your comment about the statistics, I've seen this a lot in engineering, which is they test the hypothesis by choosing the criteria and then say, okay, this is how it deviates from the other. You understand what I mean? This is a common practice I have seen. And you're right, it's very not the same way as you think of statistics often. Anyway, the thing is this, what she has done is quite remarkable in my sense, that she took this idea and translated it into a set of pedagogical tools that can be used by anybody.
Yes. Very difficult to do, and very difficult to persuade instructors to change their pedagogical approach and learn better pedagogy.
Yes. But she has made it easier by creating all of these tools and refining them over time, and with examples, and in a way it shows how you can do research. Sorry, I forgot to shut off the recording.